Okay, good morning. So we learned about sets. Now we want to talk about operations on sets. Yes? So exactly like numbers, when we learn about numbers, we learn about how to add them, multiply them, doing some algebra with them. We want to also be able to do some algebra with sets. So the operations that we want to talk about or they are complement which is an operation applied onto one single set. For example, like finding the opposite of a number. I give you a number 2, and then you give me -2. So that is not operation between two numbers. That's an operation that you apply on one single number. So you can compare the complement operation. You can have this analogy between this. I give you a set, and I ask you what is the complement of this one single set. Another operation that we talk about is called the union. Union is like addition. It should be done between two sets. And then we have another operation called intersection. And then we have another operation, which is the last one, is set theoretic difference. So usually we don't say set theoretic, we just say difference. So these are the operations that we want to talk about today. So let us start with number 1, the complement of a set. So I will just define it for you here. So definition. The complement of a set capital A is denoted by so you write the same and then you put a small letter C on top. You read it A complement. Is denoted by this symbol and is defined by so you define it in this way. You say A complement is the set consisting of all elements coming from the universal set, but such that that X does not belong to the set itself. So this is the universal set. So that's the definition. So whatever is not in A is in A complement. That's the meaning of A complement. So if I want to draw a diagram for you, Venn diagram, so let us assume that this rectangle represents the universal set. And then you have, for example, your set A here. This is your set A. Whatever is in the universal set but outside the set itself is called the complement, yes? So for example, if I want to color it, this blue region this is representing a complement. Yes, so this blue region is a complement. So the complement of a set consists of all those elements which are in the universal set, of course, as usual, but they are not in the set itself. So whenever I want you to ask you to determine the complement of a set explicitly, I have to I have to make sure that you know about the universal set. Okay, so for example, let me give a very simple example. So let the universal set be this: x in n such that x is less than or equal, 1 is less than or equal to x is strictly smaller than 10. Be the universal set. Then the complement of, for example, a is 2, 9, 7, and 4 is, so what is the complement to this? So the universal set includes natural numbers that are greater than or equal to 1, but strictly less than 10. So if you want, you can write u explicitly to imagine it easier. So what is u? U starts from 1. I am only considering natural numbers, so I have to write 1, and then I jump to 2, 3, 4, 5, 6, 7, 8, and 9, because 10 is not acceptable here. Okay, and then I close this. Now, if I want to find a complement, what I need to do, I need to eliminate elements of A from U. What is left is a complement. So 2 is in A, so I cross it over. 9 is in A, I cross it over. And the same reason, 7 and 4 are crossed over. So what is left for me is a complement. Yes, so a complement is 1, 3, 5, 6, and 8. 1, 3, 5, 6, and 8. So that is a complement. Yes. For example, can you answer this question? Let the universal set be the set of all real numbers. Okay? Then, can you tell me, so what do you know this symbol? This symbol means the set of all rational numbers. Yes. The set of all numbers can be written in the form of a fraction, whose numerator and denominator are coming from the set of integers. So that's the set of rational numbers. Okay, can you tell me what will be the complement to the rational numbers? So what does it mean? It means that for the complement of the set of rational numbers, you are interested in all those real numbers that are not rational. Yes?
The irrational numbers.
The set of irrational numbers. And the symbol for that is this. The set consisting of irrational numbers. Yes. For example, if the universal set is the set of natural numbers, what is the complement to the set of odd numbers? Yes?
Even numbers.
Yeah, the set of even numbers. This is a very simple idea, so it's not hard at all. Okay, so if I want to write a remark here, of course, this is something very trivial, but it is good to remember it here, remind it here. So, if an element belongs to a set, I can conclude that this element does not belong to its complement, yes? Yeah, it is clear. Or if it belongs to the complement, it does not belong to the set itself. On the other hand, if x does not belong to A, then if you want to, you can conclude that x definitely belongs to its complement. If x does not belong to the complement of a set, if you want to, you can make sure you are sure that this x belongs to A itself. It's very, very simple. Yes. So now let us discover some rules that are very simple. So I would say properties of the complement. So you should know about these things. Let us to understand it together. So I think it's very simple. So if I have a set, I make a complement of that set, it becomes a new set. Then I take that set and complement it once more. Then what will happen? Yes? I will get the original set back. It's very simple. If you don't understand, please let me know. But I think they are very, very simple to understand. So A is an arbitrary set. Whatever that set is, if you complement it twice, you will go back to the same set. So number 2, for example, can you tell me what happens if I complement the universal set itself? Yes?
Maybe you'll get the universal set back.
No. So the universal set complement means exactly the elements that are not in the universal set. So what happens? Might be I should ask this question first. What is the complement of the empty set?
Is it the universal set?
This is the universal set. So this means that, what is the meaning of this symbol? It means everything that is in the universal set, but is not in the empty set. But because there is nothing in the empty set, you shouldn't be worried about anything to be in the empty set. So the complement of the empty set is the universal set. Yes? And now can you just tell me what is the complement to the universal set?
The empty set.
The empty set, because nothing is left, yes? The universal set is this rectangle. You know, on the one hand, you are not allowed to go beyond the universal set by the definition of the universal set. So when I ask you what is the complement of the universal set, you have to be inside the rectangle on the one hand, and then you have to choose those elements which are not in the rectangle. This is not possible. There's nothing left. So the complement of the universal set is the empty set. So number 4. So number 4 is telling you that if I know that two sets are equal, what can I say about their complements? If two sets are equal, what happens to A complement and B complement? Yes? They are also equal. So this is very simple. I just want you to rely on your intuition. Of course, in mathematics, this could be sometimes dangerous, but not in these cases. And if two complements are equal, the sets themselves are also equal. But let me change this one now to this. Number 5. I give you two sets, A and B. I guarantee you that the first one is a subset of the other one. Now I want to ask you, is it possible to say something concrete about A complement and B complement? So I give you two sets. I guarantee you that A is a subset of B. Is there any way that you can say something concrete about A complement and B complement that is always true?
Maybe the complement of A is it belongs to, no, What was that word?
Subset.
It's a subset of the complement of B.
So what you are saying is that you can conclude this. Okay, so let us check, by the way, using the Venn diagram. Okay, so if I want to understand this a little bit better from picture's point of view, this is my universal set. I have to draw A and B in my picture in a way that I show that I respect this assumption. So how should I draw it? For example, let me draw this to be B. And then, because A is supposed to be a subset of B, I am not allowed to go beyond B if I want to draw something for A. So what should I do? This is my, for example, A. Or let me make it even smaller so that you can see the picture better. Okay, so this is, for example, A. But this is important to realize. If you want to draw a Venn diagram showing the situation, you have to respect the assumptions. A is a subset of B, so it doesn't matter how I draw A and B, but one thing is important, I have to draw A in a way which is contained totally in B. Okay, now do you think that what Gustav mentioned is correct? Yes?
No, I think B, the complement of B is a subset of B.
Yeah, so it is clear that the other way around is correct. Because if I ask you what is B complement is outside B, whatever inside the rectangle and outside B. This is what I am actually coloring here, is this one that you see in blue is B complement. But if I ask you to show me A complement, let me color it horizontally with a different color. So A complement means whatever is inside the rectangle but outside the boundaries of A. So what is that? So this is what I am doing here. I have to be careful that I have to be outside A, but I don't need to be worried about if I am outside B or not. Yes? So something like this. So the green area is A complement. So it is clear that A complement, a subset of B complement, is not working. Because when you say A complement is a subset of B complement, it means that whatever is in the green area is also included in the blue area. Blue region. Yes, it is not correct. Because this one, for example, this point, is in the green region, but it is not in the blue region. So definitely this is not correct. And so what Casimir actually mentioned is correct. So if you want to take complement from equality signs, you don't need to be worried about, you just put complements there. But if you have a subset relation, and if you want to put a complement here and there, you also have to interchange these two. Okay, so B complement is a subset of A complement. Okay, but if you want to prove this mathematically, I want to prove that this set is a subset of B of this set. So how should I prove this? If I want to prove this argument mathematically, I need to show that whatever is in this set is also in that set. So I would say that let X be an element of B complement. We show that X belongs to a complement. Do you agree? If I can show this to you, I am done. Because I want to show this set is a subset of that set. How should I do that? I have to use the definition of a subset. So I would say that choose any element you like from the set on the left and try to convince me logically that that element that you have chosen, whatever it is also in the right-hand side set. Okay, how should I do that? I have assumed that X belongs to B complement. When I say that X belongs to B complement, I can immediately conclude that X does not belong to the set itself. Yes, this is the meaning of complement. When I choose an element in B complement, it is guaranteed by definition of the complement that this X does not belong to the set itself. Okay, but now I have an assumption here. My assumption is that A is a subset of B. Now I know X is not in B. Can I conclude that X is not in A? A is a subset of B, and X is not in the bigger set. So can I conclude that X is not in A? Yes, this is logical, yes? So I can conclude that X is not in A. This is not always true, but the reason this is true is because I have this assumption that A is a subset of B. A is on the one hand a subset of B. On the other hand, I know X is an element which is not in B. So it cannot be in A either, yes? Because if it is in A, then it has to be in B as well. But if X is not in A, what can I conclude? Where is this X? X is an element which is not in A. Definitely it is where? Where? In its complement. And then I showed that this is also true. So I started from this, and I was able, based on logical arguments, to show that X belongs to A complement. So this is the mathematical proof. This is the Venn diagram justification. That is not proof. But this is also, there are many exercises in the book that you have to draw the Venn diagram to justify that something is true. So this, both of them is necessary to, are necessary to know. Okay, so this is the first operation. The second operation, as I have written there, is the union. So union means appending these lists together. Okay, so let me write definition. The union of sets A and B is denoted by, this is the symbol we use, A, and then we have this, and then this B. So some of you are doing latex, so this is called COP. This symbol you can just write like this. So A union B, so read it A union B, read as A union B. It's because there is also another symbol very similar to the union. I would recommend you, because I have seen students get confused. So when you say union, it starts with a U, and that is something similar to U. So A union B, and is defined by so we say A union B is the set of all elements. Of course, they should come from the universal set, but with some extra property. That X that you choose should be either in A or it should be in B. Okay, so this symbol here means or. And or here in mathematics is always a logical or. A logical or allows for the possibility for both of them to be true. So I don't know, everyday language, we might say that, okay, so I can buy you an ice cream or a cake. So somehow it means that I'm not going to buy both for you. Okay? This is not the way that we use or in mathematics. Or in mathematics is always inclusive. So I would say that x belongs to A or x belongs to B, it means you need to interpret it in this way always. X belongs to A but not to B, or x belongs to B but not to A, or x belongs to both of them. Okay, so when I say or, there is still a chance that both of them is also what is working. So this is the meaning of the union. I mean, the best way is probably to draw a Venn diagram first to understand this operation. So if I have this universal set, I don't know, because I haven't mentioned anything regarding A and B. So let me draw, for example, this for A. Let me also draw this for B. What do I mean by the union? The union of these two sets include all the elements in this rectangle, which are either in A or in B or in both. Okay, so where are they? So these are here, yes. Is this part acceptable?
Yes.
Yes, because these are the ones which are contained only in A. Is this part acceptable?
Yes.
Yes, because they are also belonging only to B. But this part is also acceptable because it belongs to both of them. So this green region is a representation of the union of these two sets. Okay, so this one is A union B. Okay? So, I don't know, for example, if I have this scenario, might be I have two sets. This is, for example, A, this is B. So where is the union? If I ask you to color the region or regions that represents in total the union, where do you color them? Yes?
You color A and B.
Whole A and whole B, yes? So again, these two together is A union B. Okay, so now, and if I want to give a numerical example, yes, yeah, remember that after that I will actually talk about intersection and difference. So example, so assume that I have the set A. For example, I have 2 square root of 3, 4, and 5, and I have B to be square root of 2, 5, 7, and negative 9. For example, and I want to take the union. So A union B means what? Means the set of all those elements that are either in A or in B or in both. Okay? So should I write 2 here inside?
Yes.
Yes, because 2 belongs to A. Of course, 2 does not belong to B, but it doesn't matter because of the notion of the or. So I write 2 here. And of course, you really don't need to think. You write all the elements of the first set because they have to be there. So don't worry about that. But might be you need to append some of those elements here as well. So when I reach to square root of 2, should I add it here?
Yes.
Yes, because a square root of 2 is also in B but not in A, it is acceptable. What about 5?
No.
In principle, 5 should be also here, but because I have already written that and I told you that in a set you do not repeat elements, so it is not necessary to write it down. What about 7?
Yes.
I write 7. What about 9?
Yes.
I write 9. So this is the union. So I'm appending the lists And of course, I am taking, so this is not always like in Python. So it might be in Python, when you add the list, it will consider the repetition. So it will repeat it more, okay? It depends to the operation you are doing there. So be careful. This union, we say, is not exactly identical what we are doing on programming. Okay, so this is this. But let me ask you one question. What happens if I ask you to union B to A? Instead of appending B to A, let us append B to A. A to B. So what happens then? So I start with B, for example. I would write square root of 2, 5, 7, and minus 9. And then I start appending the elements of A to this list, but I will not repeat the ones that I have already written. So should I write 2?
Yes.
Yes. Square root of 3 and 4, yes? But then what happens? A union B and B union A, are they the same sets? Yes?
Yes.
They are, because I told you that in the sets, order doesn't matter. So yes, A union B and B union A are the same. And I hope that you agree with me intuitively, this is always the case. It does not depend which sets you're looking at. So this means that, you know what is the word for it? I have used them several times. So this operation U is commutative. So it doesn't matter if you union A with B or B with A. So this means this operation that I have defined in this new world of sets is also commutative. Okay, so that is the meaning of the union. For example, if I want to write something, a remark similar to what I did before. So what happens if I tell you that X belongs to A union B, what is the conclusion coming out from this one? I am saying that I have two sets, I union them, and I see that X is an element in the union. What can you conclude from this? Can I conclude that X is in B? Is this conclusion correct?
No.
No, because it might happen that I am unlucky and X belongs to A. Okay, so this means that you cannot conclude this. You cannot be certain about that. But you can be certain about that this X is either in A or in B. And because this OR is a logical OR, in mathematical OR, it means always it might happen that this is both of them are true. And this is also important to know that this goes in the backward direction as well. So in principle, I have to put a pair of brackets around that. Okay, let me do an exercise now. Can you write, so example, can you write something about this? If I say X does not belong to A union B, what does this mean? Anyone else? Yes?
That X belongs to A union B as a complement of A union B.
Yeah, that's one thing, that's completely true. That is not what I mean here. But what you said is completely correct. And by the way, that's a good thing you said. X does not belong to A union B, because X does not belong to a set. Definitely it belongs to its complement. We will talk about this later. But that was not my point here. Might be I am not very clear. I mean, to write something similar to X belongs to A, X does not belong to A, something like this. Yeah. So that was correct. Let us write something else. Yes?
X does not belong to A or does not belong to B.
So that is the point. I want you to think about what you said. That's exactly what I want you to say, but there is a flaw in what you said. So what Casimir said, let me write it here. So he told me, if I have understood you correctly, correct me if not. You said this is the meaning of this sentence.
No, I said or.
This is or.
All right.
This is or. Yeah, that's or. Yes, Aaron?
Maybe and.
This should be and now. Okay, so that's important. Yes, so that is and. And that is crucial. Don't say that if you write or, that is wrong. Why is that? Because when you say that X is not in A union B, it means that, where is it? Let us check this picture. If forget about this one now, let us concentrate here. When I say X does not belong to A the union B, it means that X is not in the green region. Okay? If it is not in the green region, it is outside the green region. Okay? So let me just pick a point here. If I ask you to show me a point which does not belong to the green region, you might say this is your X. Yes? And then you see that this X does not belong to A and X does not belong to B. So simultaneously, it does not belong to any of them. Is that clear? Yes or no?
Yes.
Because I want to write something equivalent to this. Of course, you might say that X does not belong to A or X does not belong to B. That is not a wrong statement, but I want to write equivalency. So this means that if someone tells me that X does not belong to A union B, I can be sure that this X is neither in A nor in B. So neither nor in English means and, yes? Yes? Okay. The reason that I am saying, so for example, so of course this is a little bit logical. If I ask you to write the other way around, if I say X does not belong to A or X does not belong to B, can I conclude that X does not belong to A union B? That is why I emphasize to put "and" here, because when I say double-sided arrow, it means that if you give me, I am allowed to go in this direction, and if you give me, I am allowed to go in this direction. If I put "and", then this is double-sided arrow, that is completely correct. But if you say "or", can I go from here? If you give me this information here, can I conclude that X does not belong to A union B? Can I?
Yes.
No, I'm saying that X is not in A or not in B. Can I conclude that X is not in the union? No, because if you say X does not belong to A or X does not belong to B, it means that might be it is in one of them, not in the other one. And in that case, X belongs to the union. Yes? By the way, this is a logic. This is not. So it means that if you have problems with that, that is why you get some bugs in your codes. Because you're not thinking logically. Okay? That's exactly this. There is no teacher can teach you how to think logically, because logic is apparently in our brains. Mathematics is based on logic. Okay? We can systematize logic a little bit to understand it better, but no one actually proves that much of kind of the theorems that you think about logic itself. So for example, if I say the door is open and closed, and you realize there is something wrong going on, yes? And that's a contradiction. So this is what I want you to understand. Anyway, X does not belong to A union B means X does not belong to A. Means equivalent. Equivalent means that if you give me this is guaranteed. And if you give me these, this is guaranteed. This is the meaning of equivalency. Okay, so let me clean that one now. Any questions here? Yes or no? Okay. Now we go to the next operation, which is the intersection of two sets. I hope that you understand. I think the English word here, intersection, is already signaling what is the meaning. Can you see? I don't know. Do you understand the word intersection? Yes?
I suppose it's the middle part of the union.
Yeah, so it means that if you want to use them and on or, so how do you define that? Yes, in the middle. So we are saying the intersection, that's a good
Yeah.
English word. This means the points which are exactly here.
Yeah.
It means they are both in A and B. So that's the meaning of it. So let us just define. So definition. Okay, so let us write the intersection of sets A and B is denoted by, this is the symbol we use, A, we use this symbol, and in LaTeX it is called cap. Yes, so A intersection B, so read it as is denoted by this symbol and is defined by A. So okay, let us repeat it again together. So this is the set. Of course, the elements should come from the universal set. But which one of the elements I am interested in? Not all of them, of course. The ones that belong, yes?
X belongs to A and B.
And X belongs to B. Okay, so this is and. Okay, now I want to describe this again by the picture here. It's good. So for example, what happens if I have this? So I have this universal set. And let us assume that here, this is my A, and here, this is my B. When I ask you to color the region which represents A intersection B, it means that I am interested in all those points in this rectangle which simultaneously lies in A and in B. So this is clear that this is the only acceptable part. Okay, what about this picture? If I have A here and B here, so then what happens, do you think? Where should I hatch? Where should I color? Yeah,
There is no intersection.
intersection. So it means the intersection of A and B is equal to
Oh, the empty set.
the empty set. Okay, so here the intersection A and B is the empty set. There is a terminology here. If two sets have empty intersection, they are called disjoint sets. So A and B are called disjoint here. So this is the terminology I want you to learn. When I say I have two disjoint sets, I mean they don't have any intersections. Okay, can you also color this picture? Assume that this is my set, universal set. This is my A. B is inside now. Where should I color? Which region should I color if I am interested in A intersection B? Yes?
All of B.
Yes, do you agree? So the whole B is the intersection. And what does this mean here in this picture? You discover the rule actually, yes? So here, this is intersection B on the one hand. On the other hand, what is it? It is B. So they are equal. So you discover the rule that if B is a subset of A, then the intersection becomes the smaller set. Yeah, something like this. I mean, this is a very, very handy tool in our hands to understand sets better. But of course, this is not rigorous proof. And at this level, I mean, this is extremely important to understand it from diagram point of view, this Venn diagram point of view. Yes? Okay, now let me just give you a numerical example as before. So the numerical example is, so if I give you A to be 1, 2, and 5, and I give you B to be -1, 2, 7, and 5, then what is the intersection? A intersection B is equal to what? 1 is here but not there, I do not choose it. 2 is here and there, I will choose it. 5 is here and there, I will choose it. Of course, there is no point to look at 7. That's it. And then what about B intersection of A? B intersection A? B intersection A is the same, yes? So it shows that this operation is also, not shows that, intuitively it seems to be clear that intersection is also commutative. Okay, what I want to write from now is scattered among the exercises in the book. But it is good to actually know them as properties of these operations. Let us try to discover some of them, okay? Okay, the first thing is that, so let A, B, and C are arbitrary sets. Arbitrary sets. Okay, so the first thing we learned is that A union B is the same as B union A. We also learned that A intersection B is B intersection A. So this is commutativity, yes? You don't need to learn the names, they are not in the book, but they have mentioned these things. The second thing is that if I have 3 sets, if I union these two and find the answer, and then union it with A, hopefully you see it doesn't matter if I union A and B first, and then union it with C. Yes? The same thing is true for intersection. A intersection B intersection C is A intersection B intersection C. So this, if you want the name, is associativity, yes? Okay, so number 3. Okay, can you tell me what happens if I take a set and union it with itself? What will happen? Yes?
Nothing.
So nothing means?
It will be the same set.
The same set. So A union A, at least it is something, yes? It's a formula. So A union A is A. What do you think will happen if I intersection a set with itself? Yes?
The same set.
The same set. It's a very nice thing, yes? So if you take any set, union it with itself, it becomes itself. If you intersect it with itself, it becomes itself. This is called the idempotent property. You don't need to write those names anyway. Okay, what is your intuition here? If I take any set that you like and union it with the empty set, what do you think will happen? Union means appending things together. So what happens? I want you to, based on your intuition, answer these things based on your intuition. Yes?
Same set.
The same set. But if I take an arbitrary set and intersect it with the with the empty set, yes?
Empty set.
This time it becomes the empty set. I mean that these rules, what I'm just trying to write down are the rules of set theoretic algebra. So I'm just giving you the rules how to do the algebra with sets and these operations. Yes? They are given somehow during the among the exercises, but not as something that you're supposed to remember and apply. Okay, but this is not hard to understand. Okay, so this is it. And now let me just do this with the universal set. What do you think will happen now? So what I do, number 5, I take a set and union it with the universal set. What will happen then? Yes? The universal set. Yes? And now this is also interesting. What happens if I take any set and intersect it with the universal set? Yes?
The A set. So
The set A itself. Yes? Okay, now let us make it a little bit more interesting. I mean, it is very simple, I think. Hopefully you can answer. If I take a set and union it with the complement of the same set, yes?
universal.
The universal set. And then what happens if I do for this intersection now? What's the answer? The empty set. So you see that this everything is understandable. You don't need to memorize anything. But these are the rules of set theoretic algebra. Okay. Another thing which is not trivial now is distributivity. Okay, let me talk a little bit about distributivity in general in number algebra. So you know that we have two operations famous in number algebra, which is multiplication and addition. One of them is distributive over the other one. Which one is that? Yes? Multiplication is distributive over addition. What does it mean? It means that if I have two numbers added, and then I want to multiply the whole thing by a number, I can distribute this here and write what? A dot B plus A dot C. So this means that multiplication is distributive over addition. Okay, let me ask you the other way around. My question is that do you think that multiplication, so do you think that addition is also distributive over multiplication? This is my question. We know that this is true. We know that multiplication is distributive over addition. This means that if I have the addition of two numbers and I want to multiply a number in, I can multiply it one by one. I'm distributing multiplication over addition. So my question is that, do you think the other way around is also true? Do you think addition is distributive over multiplication? By the way, what does it mean in the first place? What I am asking you, so let me write this down, is addition distributive over multiplication? This is the question we want to answer. This is somehow related to what I want to talk about, the sets here. But do you think this answer is positive or negative, and how do you evaluate that? Can you write this in mathematical terms, what I am asking? This is an English sentence. This was a mathematical sentence. I wrote the English equivalent in front of it. Now I have started with an English sentence or question. Can you write the mathematical equivalent of this English sentence? What does this mean? Dare to say something, yes? Yes, Alexander, do you want to say something?
Addition does not distribute over multiplication.
Okay, but can you translate this sentence into something similar, a formula like this?
A plus in
A plus in
parentheses B times C.
parentheses B times C is equal to what?
Well, because it can distribute it.
Okay, but just tell me the wrong sentence.
A plus B.
Yes, A plus B multiplied by?
A times C.
No. Multiplied by? A plus C. If this was true, then it means that addition is distributive over multiplication. I told you that. I want you to translate this English sentence into mathematical symbols. This, what you see, is the translation of that. But is it true or false?
False.
It's false. You can choose numbers, for example. If I choose A to be 1, B to be 2, and C to be 3, the left-hand side is what? Is B times C, which is 6 plus 1, which is 7. And the right-hand side is what? Is A plus B 3, A plus C 4, and then this becomes 12. And they are not equal. Yes? So this means that in number algebra, we had two famous operations. One operation is a multiplication and one operation was addition. Multiplication was distributive over addition. But you didn't think about this at all, probably, because it was always wrong and the teachers didn't teach you about this. But I'm telling you that if I ask you what is the meaning of this sentence, what you said is the correct translation of this English sentence, which we realize to be false. Okay? So this is false. Okay. But now let us go back to the world of sets. And we have two operations here. One is intersection operation and the other one is the union operation. We can ask the same question or questions here. And let us see how it works here. I want you to tell me this. Okay, so again, this is not my concern if it is true or false. But I have two operations and I want you to help me to write the formulas and then evaluate if the formulas are true or false. Okay, so we have two operations, union and intersection. Okay, now I am asking you this question. Is the union distributive over intersection? Okay, I'm not saying this is true or false, but I want you to translate it into mathematical symbols. So, is U distributive over this? It might be true or false, but forget about if it is true or false. I want you to write this in mathematical symbols. How do you write that? Yes, Aaron? So A, not this little a, because in sets we use capital letters, yes? A, union,
bracket B intersects C.
B intersects C, exactly. So you understand, that is my concern. I want you to understand what I mean by this English sentence, yes? Is equal to what?
A union B intersects A union C.
Yes. When I ask this English question, it means check this. We don't know if it is true or false, but I want you to understand if union is distributive over intersection, it means this. Do you agree? Let me just practice once more. Is intersection distributive over this? This might be true, might be false, but let us assume that I want to write the mathematical symbols for this, mathematical translation of this question. So the question mark is here now. Okay, so what should I write here now? Anyone else? Okay.
It will be A intersect bracket B union C
Exactly.
equals bracket A intersect B union A intersect C.
Yes. And the question mark comes here. That is important, by the way. Both of them are in your book. Okay? And the answer to both of them is yes. So, in the contrary, here when I was working with numbers, one of them was distributive over the other one, but not the other way around. But when we will see that a little bit, I will try to justify it for you, that this is always the case, this is also always the case. This kind of algebra is called a Boolean algebra. Boolean algebra, yes? George Boole was the inventor of these kinds of things. So Boolean algebra. And that is the main difference between a Boolean algebra and the algebra we had before. So here we have two operations. Each one of them is distributive over the other one. Okay? So let us try to analyze these problems a little bit together. Okay? If you want to prove it rigorously, it is beyond the scope of this lesson. But you can motivate yourself why this should be correct by Venn diagram, for example. Of course, Venn diagrams are not mathematical proofs, but they are very close to reality, yes, especially for simple cases. This is something, I think this is one of the exercises in the book, something similar to that. We want to motivate us that this is true. This is the first time that we want to use Venn diagram to somehow justify equality. So it means how many Venn diagrams I need? I need two Venn diagrams. I need to draw a Venn diagram for the left-hand side. I need to draw another Venn diagram for the right-hand side and then compare them. Yes? So where should I start? Because I have three sets involved. So let me just draw a big rectangle here and call it the universal set. So let me make it simple. So here is A. If I want to consider the most general possible case, probably it is better to have some overlaps between all sets. Okay, I cannot do it with my hand, but you need to carbon copy exactly the same picture 2 times, yes? Yeah, you have to have the exact version of that one here as well, but we can pretend that I have done the good job. Okay, so let us, for example, I don't know which one is better to start with. Let us start with this one. When I say A union B intersection C, I am facing two operations, but the priority is with which one? The rules of mathematics are the same. So which one has the priority?
B intersect.
Because it is in the pair of brackets. So I want you to tell me where should I color if I mean B intersection C. So this circle represents B, this circle represents C. When I say B intersection B, I want to look at the overlap between B and C. So where is that? So I color this one. So this is so far not the whole story, but this is B intersection C. And now I have to union it with A. So A is this circle. I want to union this circle, the points in this circle, with this colored region. So what do I get? I need to color these areas as well because they are in A. I want to append these areas. Okay? So this is also A. Of course, A also goes inside. So this orange one is just A. Okay, so if I ask you, what is the union between this orange region and the green region in total? There are some points which belong to both of them. Some points only belong to A, some points only belong to B intersection. I need all of them. So I don't know if I can do that. So let me just try to draw the boundary for it, yes? So A union B intersection B, I hope that you agree with me. If not, let me convince you that this yes, this is what I have, yes? This whole boundary that you see is A union B intersection C. Do you agree? Whatever is inside this black boundary is this expression. Yes? Understandable? Okay. Now we go to the right-hand side. So this was the left-hand side. Now let me just do this on the right-hand side. So the right-hand side, I have A union B. It's a little bit messy, I agree, but I hope that you can convince yourself at the end. So let me change the color. So A union B, where is it? A union B is the whole parts which are only in A or only in B or both in A and in B. Okay, so do you agree that what I have done here is A union B? Yes? This is A union B. But now I want to have A union C. Here, you see, this is A union C. So A union C, I change my color. I focus on N, A, and C. I have to color all parts which are only in A, only in C, or in both. So where are they? So I don't know. Let me just try to draw this in this way. I also have to go here. Yes, do you agree? So these parts that I am coloring now in orange, I hope that you understand what's going on. So this is A union C. Okay, but now what I am supposed to do, I am supposed to make an intersection between the previous colored region in green and the new colored region which is in orange. So I take again my black pen and try to draw a border around it. So can you see where is it? When you say intersection, you are interested in those areas which have two colors, those areas. So do you agree with me that is exactly the same? Because this part contains two colors, yes, and then this is also containing two colors. But then you see this part also contains two colors. Yes, it's not a very good picture, but hopefully you understand what I mean. I am not allowed to consider this as my inside the border because it contains only one color. I am not allowed to include this part because it contains only one color. And then hopefully you see that these pictures are now identical. So this means that A union B intersection C, at least in this picture, is exactly equal to A union B intersection A union C. So this is a very big deviation from number algebra. In number algebra, we have one of the distributivities without having the other one, but here we have both of them. Okay? It's Boolean algebra. Okay, I don't want to continue the lesson. I would recommend you to try to justify this one exactly with another picture for yourself to understand this method. And then we will continue the rest of the lesson later, okay? There are many things we want to discuss. There is one operation left, and that is the difference of two sets. But before reaching to the difference of two sets, there are many things we can discuss about up to this point. Okay, any questions? No? Okay, thank you.